We've done calculations with densities of solids and liquids, and typically when you're doing a solid or a liquid, densities are reported in grams per milliliter. For gases, however, densities are usually reported in grams per liter because gases are not very dense. And of course, the formula for gas doesn't, it does depend on the mass and the volume, but it also depends on pressure and temperature. This is the formula for density of a gas. D is equal to PM over RT, where D is density. P is still pressure, R is still the ideal gas constant, 0.0821 liters atmospheres per mole Kelvin, and T is temperature. Pressure needs to be in atmospheres, temperature needs to be in Kelvin so that those will match the units for R. M, it's a cursive M. M is for molar mass, not to be confused with this M, which if you'll recall stands for molarity. Cursive capital M for the molar mass. And so this is the problem we're going to work. We're going to calculate the molar mass of 19.3 grams of a greenish yellow gas that has been produced in a 2.5 liter vessel at 36 degrees Celsius and 2.88 atmospheres. And I've just copied the problem on the next slide. So, if we know that our formula is D is equal to PM over RT, let's go ahead and rearrange the formula to solve for molar mass. So we can isolate that variable on one side, and our algebra shows us that the molar mass would be equal to dRT over P. We know what R is. We know that the temperature is 36 degrees Celsius. We can easily convert that to Kelvin. The pressure is already given to us in atmospheres. So what is D? We're not given the density of the gas, but density is still mass divided by volume. And so we know for D that the mass is 19.3 grams and that the volume is 2.5 liters. And so we can calculate the density, and we'll have that the density of this gas is 7.72 grams per liter. And now we can plug that into this formula. M is equal to dRT over P, where D is 7.72 grams per liter. R is 0.0821 liter atmosphere per mole Kelvin. I'm running out of room, so I'm going to squeeze that in. The temperature is 309 Kelvin. Okay, all those are multiplied together, divided by, there's a decimal there on the pressure, a pressure of 2.88 atmospheres. And that will give us that the molar mass of this gas is 68.0 grams per mole. And that's just one way to use the density equation. Of course, sometimes you could be given the gas, the identity of the gas, and asked to solve for the density. And all you would need is the formula of the gas, and you could calculate the molar mass. Now, another type of problem, going away from density and moving to another gas laws concept, is gas stoichiometry. And you'll recall we've already completed a section on stoichiometry where we use coefficients in a balanced equation and convert from grams of one thing to moles, and we can compare moles of two different components of a reaction. NaN3 is sodium azide. Upon heating, sodium azide will very rapidly break down into sodium metal and nitrogen gas. And then, of course, we would need to balance that equation. And there it is, balanced. This is the reaction that's used in automobile airbags. Nitrogen gas is actually what inflates the airbag, and sodium azide is just a white solid in there that upon collision, there's a steel ball on an inclined plane, and if the collision's strong enough, it compresses a spring, and this ball strikes a plate that gives off a spark. Sodium azide is ignited, and of course it's an extremely rapid decomposition, and nitrogen gas is what fills the airbag. The white powder is just when the airbag deploys. Now that's just cornstarch to keep the airbag from rotting and having holes in it. There's a second reaction that has to happen to take care of the sodium, because sodium metal around is not a good idea. If you'll recall, group 1 metals, like sodium, are extremely reactive with water. So you do have to have a secondary reaction that takes care of the sodium. Okay, so what we're going to do is use some of our stoichiometry along with our gas laws concept of PV equals nRT. Let's calculate the volume of nitrogen gas given off when 48.6 grams of sodium azide decomposes at 32.5 degrees Celsius and 1.10 atmospheres. Okay. We are given an amount of the sodium azide, 48.6 grams. Now realize the sodium azide is a solid. A lot of people, what they will try to do is convert this to moles and then plug that straight into PV equals nRT. But PV equals nRT is an ideal gas equation. That equation can only be applied when a substance is a gas. So we're starting with an amount of sodium azide. We're asked to calculate a volume of nitrogen. Nitrogen is the gas. So this is where we're going to use PV equals nRT. We're looking for a volume of nitrogen. So V is what we're looking for. We are given a pressure. Okay. We are given a temperature. We know what R is. So we have almost everything we need to solve for volume except for moles. We don't know how much nitrogen we're going to make. We can calculate that using stoichiometry, because we know that if we start with 48.6 grams of sodium azide, we can calculate how much nitrogen we'll make if we know how much of the reactant we have. And our first step would be to convert this to moles. The molar mass of sodium azide is 65.02 grams. And I know from the balanced equation that I will generate 3 moles of nitrogen for every 2 moles of sodium azide. Of course, I'm using my coefficients from my balanced equation there. And I plug that into my calculator. And I calculate that I will produce 1.12 moles of nitrogen. And so now I have my moles for this equation. I can just solve for V. And V is going to be equal to nRT over P. I just calculated my moles. It's 1.12 moles. R is 0.0821 liters atmospheres per mole times Kelvin. The temperature that I'm running this at is 32.5 degrees Celsius. I've got to be sure and convert that to Kelvin. So I add 273.15. My pressure was 1.10 atmospheres. And so I know that this will produce 25.5 liters of nitrogen gas. Okay, one other concept I want to point out that relates to this stoichiometry, it's the law of combining volumes. And if you'll recall, we introduced the gas laws and introduced Charles and Gay-Lussac's law. And we said that they compare volume and number of moles. And we said that volume and number of moles are directly related to each other. Well, a very important relationship that we can use from this equation is that if we are at constant temperature and pressure, because remember when we dealt with the ideal gas law, we always compared two variables and then there were some things constant. But what this allows us to do is to use the coefficients in an equation. For example, if we look at the reaction of hydrogen gas and oxygen gas to produce water, and then we look at balancing that equation, we see that this is that balanced equation. If we're at constant temperature and pressure, and we know that these coefficients mean moles, okay, and I'm only going to be right now looking at comparing the hydrogen and oxygen because those are the gases in this equation, okay. Water's a liquid, so we're not going to use Gay-Lussac's law here. But at constant temperature and pressure, what these coefficients allow us to do is to not only compare moles, but to convert that straight to volume. So in other words, if we had 10 liters of hydrogen, how many liters of oxygen would react with that? 5 liters. Okay, we know a direct comparison. Those numbers can also mean moles as well. If we had 4.8 liters of hydrogen, then we know that that would require 2.4 liters of oxygen. Okay, and that's the law of combining volumes, which says the volume ratio of any two gases in a reaction that's at constant temperature and constant pressure is the same as the mole ratio.